Okay. Uh, so first of all, I guess the most important thing that everyone wants to is thinking about is the final. So exam 5. There are 2 times you can take it. And if you can't, if you have a problem with both of these, talk to me right away, and we'll figure something out. But um, the night class has it scheduled for Monday. That's at 6 p.m. in the room one over from here. So uh, S1326. And then the day class has it scheduled for Thursday, so a week from today, at, I just told people, damn it. Well, you guys are at 2 p.m., and that's in this room. I just told my last class that theirs was at 2 p.m. I got mixed up. I have to correct that. You don't have to worry about that. And the topics are everything that we've discussed up through right now. So so that's up through conservation of linear momentum and conservation of mechanical energy. Okay. Um, for the people who are taking physics 2, and also for the people who are getting ready for like standardized tests where you're going to have to do physics, we failed to get through a topic that that you're going to want to know something about. And so I was planning to talk about that today, but what I've done instead is I've just posted the last 2 lectures from last year, um, on D2L, along with all the other lectures, and it'll be, if you look at it, it'll be easy to see which ones I'm talking about. And then I put a link to the videos from last year. So if you want to just understand a little bit about what rotational motion is like, and it's not like it's going to be a huge thing in the next semester, but um, you want to have seen the words and gotten some sense of, then I would say just go through those lectures when you have a chance and don't kill yourself over it, but try to understand some of the ideas, and I think it would pay off. Okay, so yeah, today, instead of going through rotational motion, I'm just going to I'm going to answer questions that you have, maybe make up a couple of questions if you don't have that many, and then that's it for the day. Okay. So first, does anyone have any homework related questions or types of questions that you'd like me to, I could make some questions up and you could work on them together? I'd be sort of happy to approach those however you want. Yes. Number 11 on conservation of energy. Do you have it with you? I don't have it in front of me. Yeah. Okay. Uh, I assigned number 11 and it says elastic. Then that was a mistake. So I need to correct that. We didn't do elastic collisions. We only did inelastic collisions. But let's do one like that with an inelastic collision. Okay. So there's no elastic collisions. All right. So there's a hill. Is that right? It starts out on a hill and then they roll up a hill at the end. Um, The hill was on the other side. Yeah, it doesn't matter. Um, and let's do it this way. So let's say there's a 1 kilogram cart up here, and it's going to roll down the hill, and it has a little latch on it. And when it gets to the bottom of the hill, it's going to run into another cart. Let's say the other cart has a mass of 0.5 kilogram. And it has a little latch. And so when they collide, those, they're going to latch together. And from that point on, they're going to move with the same velocity. So that's an inelastic collision. So 1 kilogram cart rolls down the hill and latches to a 0.5 kilogram cart. And we want to know what's their combined velocity after the collision. We need to know the height of the hill. So let's say that the hill is 1.5. Actually, let me change. Let's say the hill is 2 meters high. Okay, we're going to do this problem in 2 parts. And the way you know how to separate the problem into parts is conservation of linear momentum is only going to be used in any problems for the collision itself. So conservation of linear momentum just represents the instant right before the collision until the instant right after the collision. Okay. So that means that conservation of energy is going to be used to go from the instant the cart starts rolling down the hill till the instant right before the collision, and then conservation of linear momentum after. So until right before the collision, we're going to use conservation of mechanical energy. And then the collision itself, so going the instant before the collision until the instant right after the collision, we're going to use conservation of linear momentum. So part 1. So this is the conservation of mechanical energy part. So first of all, you have to think, can we use conservation of mechanical energy? It's not so important. I mean, like, I already told you that we're going to use it. So, right now, there's not really any reason to think about that. But if you see a problem like this on a test or something, with no other context, you have to figure out whether conservation of mechanical energy is a valid way to approach it. And so you have to think about, are there any non-conservative forces that do work during this time interval? Okay. So let's think about what forces are acting on this cart as it goes from the top of the hill to right before the collision. Okay. So what forces are acting? The weight. That's okay. We have a potential energy function for that. There's one other force that's acting, the normal force. And the normal is non-conservative, but it doesn't do any work. So that's fine, okay? So there's one non-conservative force. That's the normal force. But the work is 0 for that one. So conservation of mechanical energy works for this. So we can set it up. Instant 1 is going to be when it's at the top of the hill. Instant 2 is going to be right before the collision. At the top of the hill, we have to figure out the gravitational potential energy. To do that, we have to choose a height equals 0 location, and we might as well choose where they are when they're on the flat, although you can choose anywhere you want as long as you're consistent through the whole problem. So the gravitational potential energy is the mass times 9.81 times the height. So that's 19.62. And what are the units? What are the units of potential energy? We're in SI units. So what are the units of energy in SI units? What? It's newtons times meters. It's joules. It has its own name. So. And then the kinetic energy is 1/2 times the mass times the speed squared. What's the cart's speed at the top of the hill? Yep. And then right before the collision, the gravitational potential energy is 1 kilogram times 9.81. What's the height? 0. Because now it's down on the flat. So 0 gravitational potential energy. And what do we know about the kinetic energy? It's 1/2 times the mass. What do we know about the speed? We don't know it. And we have to calculate that to go to the second part. So right, just leave that as V. And so the kinetic energy is 1/2 V squared. So then we can plug this into conservation of mechanical energy. It says 19.62 plus 0 is equal to 0 plus 1/2 V squared. So V squared is equal to 39.24. And what's the square root of that? Okay, so right before the collision, the speed of that cart is 6.26 meters per second. Yes. I don't think I would mark you off for that, but I do try to tell myself to do that. Okay, so that's the end of part 1. Now we have the speed that we need to go on to part 2. So part 2 is the collision. And I said it's usually a good idea to do these collision problems, conservation of linear momentum, using a view from up above. So I'm going to do that, a top-down view. So on the left is the 1 kilogram cart that's coming in with a velocity of 6.26. On the right is the half kilogram cart that has 0 velocity before the collision. The coordinate system I'm going to use has the x-axis in the direction of motion. So that makes it easy to represent that as a velocity vector. And conservation of linear momentum for an inelastic case, that means that after the collision, they're going to have the same velocity. The linear momentum of the 1 kilogram cart before the collision is the mass of 1 times 6.26 in the positive x direction and 0 for y. The linear momentum before the collision for the half kilogram mass is 0.5 times, it's at rest, so the velocity is 0, 0. And then after the collision, they're going to be moving as a single object. So the combined mass is 1 plus 0.5. And we want to calculate the velocity vector, Vx, Vy. The x equation says 6.26 is equal to 1.5 Vx. And so Vx is, what's 6.26 divided by 1.5? 4.17. And the y equation says 0 is equal to 1.5 Vy, so Vy is 0. And so after the collision, the velocity vector is 4.17 in the x direction, 0 in the y direction, meters per second. So hitting the, the heavier mass, the heavier part coming down the hill and hitting the lighter one slows it down a little. That's how much. Yes. No, we can't. I didn't go into how to do that. That's called an elastic collision, and it sounds like that's what you have to do in number 11. So so don't do number 11. That's all we can do. We didn't talk about any other kinds of collisions. But you can imagine. So conservation of linear momentum, I said last time, doesn't give you enough information to solve the problem unless you know something about the collision itself. And so you can imagine that what you know about the collision itself can take a lot of different forms. It just has to be some kind of relationship between the velocities before and after the collision. And then you can solve it as a system of equations. I did this one because this is the easiest way to combine the requirements. You just, after the collision, you just add up the masses and treat it like it has a single velocity. Any other problems that you'd like to see? Oh, I thought you were raising your hand. I was so excited for a second. Okay, well, let me just make up a couple. Let's do some, I don't think we've done one where something's swinging in a circular motion. So let's do one where there's a mass swinging around in a circle. That's almost a circle. Let's say it's going counterclockwise, and say this is up, so weight's acting toward the bottom of the page. And let's say that at the top of the at the top of the path, the speed of the ball is 4 meters per second. And let's give this a mass. Mass is 1/10 of a kilogram. That's a side view, yep. That's right. So let's figure out the speed of the ball at the bottom of the path. And then, so remember, we talked about this just briefly in lab, but what's the criterion for whether this ball is speeding up or slowing down in a problem like this? What determines whether it's speeding up or slowing down? Yeah, well, so what I'm looking for is just whether it's rising or falling. You know, on the way up, it's slowing down. On the way down, it's speeding up. And so at the bottom of the path and the top of the path, those are the only two instances where at that instant the speed isn't changing. Okay. So what I'm getting at is at the bottom where we're going to calculate the speed isn't changing. What's the tension in that string? Yeah, the bottom is where it has the greatest amount of tension. So for part A, we're going to use conservation of mechanical energy. And for part B, this is a circular motion problem. If the speed isn't changing, what kind of circular motion is it? Remember, I split it up into two kinds of circular motion, one where the speed isn't changing and one where it is changing. Uniform circular motion, yep. Tetherball is an example of a uniform circular motion. This isn't a tetherball problem because a tetherball is a circle that's parallel to the ground. This is like a Ferris wheel. Okay. Yeah. Yeah, I think I assigned at least one tetherball problem in the homework, right? So that is fair game. Okay, so first, for part A, that's the path. We know that up here the speed is 4 meters per second. Oh, and I need to give a length of this string too. Let's pretend I already did that. And when I did that earlier, let's pretend that I said 0.4 meters. Okay, so up at the top of the path, the speed is 4 meters per second. And I'm going to call this instant 1. It doesn't matter what order you call these. And we're trying to figure out the speed down here. So this is going to be instant 2. Okay, how do you know that we can use conservation of mechanical energy for this problem? What forces are acting on the ball? at just some arbitrary instant in here. The weight is 1, that's right. Not normal tension, the force the string applies to it. So it's just being, spun around like this. So a normal force would be if it's like in contact with the surface. Okay, so the forces are the weight. That's fine. We have a potential energy function for that. And the only other force is the string force. Yeah. And so, right, it's tension. So now we have to think about whether that does any work. And in this case, in any case where something's moving around in a circular path, any force that acts towards the center of that circular path does no work. It's a centripetal force. And notice that's what this string does. Okay, like if I drew the force vector applied by this string, it's right toward the center of the circle, which is here. And so it doesn't do any work. So that string force is centripetal. Yes. Yes, exactly. Yep. So at every instant, the velocity is tangent to that circle, and the string force is toward the center of the circle. So they're perpendicular. Okay, so now we can set it up. Instant 1 is at the top. Instant 2 is at the bottom. Gravitational potential energy is mass of the object. So that's 0.1 times 9.81. And now times the height. And we have to choose a 0 height. And like always in these problems, it doesn't matter where you choose it. It just matters that you're consistent through the whole problem. So I think people would probably choose two different answers. They would choose either the bottom of the circle or the center of the circle. Either one of those works out fine. Might as well choose the bottom, I suppose. I usually choose just the lowest height that occurs in the problem. So I'll make that h equals 0. So what's the height at the top at instant 1? That's right, 0.8. 2 times that radius. And so this is 0.7848, I think. And the kinetic energy at the top is 1/2 times the mass, 0.1, times the speed squared at the top. The speed is 4. So you get 0.8. Okay, and then at the bottom, at instant 2, gravitational potential energy is the mass, 0.1, times 9.81, times the height. What's the height at instant 2? So 0 potential energy. And the kinetic energy is 1/2 times the mass times the speed squared. What do we know about the speed? We don't know anything, so I'm just going to leave it as v squared. And so I'll write that as 0.05 v squared. And so conservation of mechanical energy says 0.7848 plus 0.8 is equal to 0 plus 0.05 e squared. So let's see, 1.5848 is equal to 0.05 v squared. So can someone tell me what v is, or v squared? 31.696, and then the square root of that? 5.63 meters per second. So if the speed's 4 meters per second at the top of the circle, it has to be 5.63 at the bottom of the circle. According to this model, which is, simplifies some things, but that's pretty accurate. Yep. Oh, okay. So that second 0.8, so in the gravitational potential energy, it's the height, but it's also just happens to be equal to the kinetic energy. That's just how the numbers came out. So that's just 1/2 times the mass times the speed squared. Yes. Yeah. Okay, so that's part A. We know the speed at the bottom. So now we're going to use that for part B. Now we have a circular motion problem. And I'm going to put the coordinate system like this. And we're going to analyze what's happening at the bottom. If it's spinning this way, then the velocity vector would be like this. And speed is 5.63 meters per second. The centripetal acceleration goes towards the center. And so the centripetal acceleration is in the positive y direction. That means it's equal to 0 positive v squared over r. And so that's 0 for x, 5.63 squared divided by 0.4 for y. And what do you get for that y value? Oh, 31.696 divided by 0.4. 79.242. What about the tangential acceleration? There is none because the speed isn't changing. So the total acceleration is 0, 79.242. And now draw a free body diagram. What forces are acting on the ball? Yep. So that's the mass 0.1 times 9.81, so 0.981. And one other force, what is it? The tension, and what way does that point? Toward the center, yep. And that is a value t. We don't know what that is. Now Newton's second law says 0t plus 0 negative 0.981 is equal to the mass 0.1 times the acceleration 0.79.242 The x equation doesn't give anything, but the y equation says t minus 0.981 is equal to 0.1 times 79.242, so 7.9242. And so t is equal to 7.9242 plus 0.981. That's too hard for me. 8.905 newtons. And so if you have this thing with a mass of 0.1 kilograms and you know the speed at the top, this calculates the force that the cable has to apply at the bottom to keep it moving in that circular path. And so if you don't have a string that can support this, it'll break when the thing gets to the bottom. And that's the only place, like, that's where that tension is the greatest. So this tells you, you know, based on how strong the string is, whether it's going to break or not. So it's a uniform circular motion problem because of that particular point. Exactly. Even though on the rest of it. Yep, that's exactly right. There are, yeah, so in a circular motion like this, where it's sideways like a Ferris wheel and the only thing connected to it is a string, there are two places where the speed isn't changing, exactly at the top and exactly at the bottom. And everywhere else, at those two places, it's uniform circular motion, but every other place, it's non-uniform circular motion. So the good news for us is the places where we most want to calculate the tension are the top and the bottom, because that's the lowest force and the highest force applied to the string. Okay, let's do one with a spring. Okay, so let's say there's a spring here. And it's pressed against a mass, let's say this is 5 kilograms. Let's say the spring has a constant of 1,000 newtons per meter. And we pull the spring back 0.05 meters, so 5 centimeters from its resting length, and let it go. How high will that mass get up the hill before it stops and starts coming back down? So how high will the cart make it up the hill? Yes. Yes. Every equation will be given. Yeah. Okay. So in this problem, I think it's always a good idea to make sure for yourself that you can use conservation of mechanical energy. So let's think about the forces that are acting in this problem. So someone lists one. First person gets the easy one. Hey. Yep. So the spring force, and then there's only one other one. Normal. Yep. Okay. So these are both conservative. We have potential energy functions for those. Those come up in, at least one of those comes up in every conservation of mechanical energy problem. So we're used to seeing those. The normal force is non-conservative, but the work is equal to 0. So we have what's required to use conservation of mechanical energy. There's no non-conservative forces that do work. So now we can split it up into instant 1 and instant 2. And we've done one problem like this before, but now we have to represent the potential energy. At each one of these instants, we have to represent the potential energy due to the spring and the potential energy due to the weight. At instant 1, we haven't chosen a height equals 0, but I would always choose it at the height of the thing, at at its lowest height. Okay, so the potential energy due to gravity is the mass times 9.81 times the height of 0. And so there's no gravitational potential energy at instant 1. 5 kilograms. And then the potential energy of the spring at instant 1 is 1/2 times the spring stiffness, and I gave that as 1,000, times how far the spring is stretched or compressed from its resting length. And I think I gave that as 5 centimeters. Yep. Squared, so 0.05 squared. So that is, I think, 12.5. And then the kinetic energy, when you release it, you're just holding it there. So it doesn't have any speed at the instant you let go of the plunger. So the kinetic energy is 1/2 times the mass times 0 squared, so 0. Anytime something's at rest, it has 0 kinetic energy. And then at instant 2, the gravitational potential energy is the mass times 9.81. It's the height. What do we know about the height? Yeah, we're trying to find that, so I'll just leave that variable h. So this is 49.05 h. And then what do we know about the spring potential energy? Well, once the spring top stops touching the object that you care about, there's no more spring potential energy. It doesn't, once the thing's gone, you could be compressing or stretching the spring. That doesn't have any effect on the thing that you're analyzing anymore. So the spring potential energy is 0. And then the kinetic energy is 1/2 times the mass. And what's the speed when it gets to the highest point on the hill? Yep, slowing down. It gets to its highest point, it stops for an instant, and then it starts coming back down. So times 0 squared. Yes. Yeah, but just don't get confused if it's like, so the spring comes back to its resting length. Or, I mean, imagine, so the spring would actually overshoot a little bit, and so maybe it goes this way and then oscillates for a little while, all the carts going on. And then say you have the information about where that spring was in its oscillation. So you're like, oh, do I need to use that? No, because it's not touching the object anymore. Okay, so conservation of mechanical energy. We have 0 plus 1.25 plus 0 is equal to 49.05 H plus 0 plus 0. And so H is 1.25 divided by 49.05. So what's that? 0.025 meters. So 2.5 centimeters up the hill. And now, which of these two things is that telling us? Is it telling us this distance is 2.5 centimeters? Or this distance is 2.5 centimeters? The second one. So that gravitational potential energy doesn't tell us anything about how far it'll go. And if this was a more gradual hill, as long as there still was no friction, this would go 16 miles if it had to change its height 2.5 centimeters. That's not realistic because there's always enough friction that something would stop before that. But we're always assuming that there's no friction, and so that distance just doesn't matter at all. Yes? No, you don't have to show it, but just interpret what's... Yes? Yeah. Right. Yeah. The reason is that right now, since all the problems we're doing are conservation of mechanical energy, it's obvious that that's the way to go with this problem. But some problems that are good for conservation of mechanical energy look like problems in many ways that are not good with conservation of mechanical energy. So this is one way to figure out what approach you want to use for a problem. No, I don't think there are. Yeah, but so the easy answer is this. We only have 4 kinds of forces that we can work with conservation of mechanical energy: weight, spring force, normal force, and centripetal force. If you have anything other than those 4, you can't use this approach. I mean, you can use this approach, but not with the detail that we've gone into. Yeah, if you study energy methods farther than this, then you start talking about the work done by non-conservative forces, and you see that that this can be extended. But the way we're doing it, you're just stuck if you have anything other than those four forces. Yes. Yeah. Yes. And right. Yes. Um, uh-huh. Exactly. And yep, exactly. So and the reason that it works like that is uh, when you look at the equation, I mean, we happen to put the, I'm just in the habit of putting the earlier stuff on the left side of this equation and the later stuff on the right side. But this method doesn't differentiate between what happens before or after. I could easily put this over here and that over there. And so this equation works equally well for either one of those two cases. All it knows is there's an energetic kind of equivalence between being 2.5 centimeters up the hill and having that spring compress 5 centimeters. That's right. You know H and you look for X. Right? Yeah. Um, uh, you know, um, so if I just, yeah, if the question said this cart starts 2.5 centimeters up the hill, how far will the spring compress? Um, okay, yeah, let me go through that because actually, so um, for this equation to exactly be the same, the equivalent question would be, um, how high would you have to start the cart up the hill for it to come down and compress the spring 5 centimeters? Then the equation looks exactly like that. Okay, so so now let's say that it starts 0.025 meters up the hill. How much does the spring compress? It's all the same forces, so conservation of mechanical energy still applies. Instant 1 is when it's at the top of the hill. Instant 2 is when the spring is compressed. Okay, so at the top of the hill, the gravitational potential energy is the mass, 5 kilograms, times 9.81, times the height of 0.025. And I'm going to guess that that's 1.25 joules. Then that, yeah, it's, so there's round off here, but this has to be the same amount of energy that we had before, because what we figured out in the last problem was you have the same amount of potential energy compressing the spring that much as you have having it this high up the hill. Okay, so, and then what's the spring potential energy at instant 1? Yep. And the kinetic energy, that's 1/2 times the mass times the speed squared. What's the speed? 0, yeah. So anytime something's at rest, there's no kinetic energy. And then at instant 2, what's the gravitational potential energy? Yep, the height is 0, so the gravitational potential energy is 0. The spring potential energy is 1/2 times the stiffness, 1,000, times the amount the spring is deformed, squared. So I'm just going to leave that as x squared. We're going to calculate that x. And then what's the kinetic energy? 0. Yep. So conservation of mechanical energy says 1.25 plus 0 is equal to 0 plus 500x squared plus 0. And that is, yeah, exactly. So is that going to come out right? So x is equal to 0.05 meters. And what would it calculate if now we did another instant where we said there was no gravitational potential energy and no spring potential energy and set it equal to these? Can you think what instant in that motion we'd be calculating? So that would be saying, right, that would be saying that it hasn't touched the spring yet, but it's all the way down the hill because the height is equal to 0. And so it would tell you how fast this thing would be going. We could calculate how fast it's going along the flat right before it hits the spring. Any other questions about that one? Yeah. No? Okay. Yeah. Okay, so let's say a 10-kilogram cat is swung in a circle by his tail. Yeah, I know it is. Too bad. It'd be a lot more comfortable if it wasn't so heavy. Okay, so it's going in a circular path like this. Here's the center of the circle. So let's say the angle between the cat and the horizontal, between the tail and the horizontal, I guess, is 40 degrees. What are the speed of the cat and the tail tension? We need the tail length. Yes, very good. So the tail length is, it's a good cat tail length, 0.6 meters. That's after you've been doing this for a really long time. Let's say 0.2 meters. Okay, so um, this is a tetherball problem. And so we're going to take a side view. This angle is 40 degrees. The hypotenuse of this triangle is 0.2. And so this distance is the radius. And that's 0.2 times the cosine of 40. So that is, can I do that in my head? Maybe that's 1.532. 1.532. Oh, 0.1532. Okay, so that's R. We're going to choose a coordinate system in this orientation. Which way does the centripetal acceleration point? Toward the origin there, just straight in the negative x direction. And so that's in the negative x direction. So this is negative b squared over r, and then 0 for y. So we can write that as negative b squared over 0.1532, and then 0 for y. Tetherball problems are always uniform circular motion, so there's no tangential acceleration. So the total acceleration is negative v squared over 0.1532, 0. So now free body diagram. There's a weight down of, what did I say, 10 kilograms? So 98.1. And then the only other force is a tension in the tail. So we have to figure out the angle for that force. That force is over here. And this angle is 40 degrees. So that force is T times cosine of 140, T times sine of 140. So that's negative 0.766 T, positive 0.643 T. Yes. It's 40 degrees short. I said the angle was 40, right? So it's 180 minus 40. Each one of those is 90. So you're thinking of a 270, I think. Yeah, 180 minus 40. So Newton's second law says 0, negative 98.1 plus negative 0.766 T, positive 0.643 T, is equal to the mass times the acceleration, which is negative v squared over 0.1532, 0 for y. So first, the y equation says t is equal to 98.1 divided by 0.643. What do you get for that? 152.566 newtons. And then plug that into t in the x equation. So negative 0.766 times 152.566 is equal to negative 10 over 0.1532 v squared. So it's going to come out positive, which is good because that's squared. You can't have a negative variable squared. That's for v or v squared. 1.79 meters per second. And so v is square root of that. This is 1.34 meters per second. So somewhere around like between 3 and 4 miles per hour. Any questions about that one? Okay, yes. So the for any circle, so except for tetherball problems, you always choose a view where you can see the circle. Okay, so if there's any horizontal problem that's not a tetherball problem, you want to take a top-down view. Any other questions? Okay, thanks for taking my class. So yeah, let me know if you have, oh, my office hours next week are gonna be the same as my office hours during the semester. If you can't make it to those, send me an email and I'm sure we can arrange another time. Okay, all right, see you next week.